All right, this is lesson 7.4. It's about waves. Specifically, it's about the waves of light in the electromagnetic spectrum. We're going to look at the dual wave particle nature of matter and energy. That is, matter and energy can both exist as waves as well as particles. So we'll look at how can an electron be a wave and how can light be a particle. So why should we study the EM spectrum or the electromagnetic spectrum? So we can understand how electrons and photons behave and interact, which helps us understand the quantum mechanical model, how the atoms put together. And it also helps us with atomic emission spectrum, which you did study last year and we will be expanding on this year. And we can also use light as an analytical tool. It's called spectroscopy. So it's a way that chemists can analyze chemicals to find out the identity of the chemical, is to use spectroscopy. Lesson 7.5, which is PES or photoelectron spectroscopy, is a whole area of analysis. It's an analytical tool. We'll study that. And then labs 11 and 12 are a different type of spectroscopy that we'll look at. So looking at the electromagnetic spectrum, you could see I have microwave, infrared, visible, ultraviolet, and X-rays listed across the top there. And those are listed in order of increasing energy. So my arrow pointing towards the right says I'm increasing in energy. So you do need to know what order they come in order of increasing energy. So you may already have a way of remembering this, which is totally fine, but I'm going to tell you mine just in case you need one. So I'll start with visible light. Visible light is abbreviated VIS. And this is what we usually just think of as light. When we say light, this is what we mean, the light we can actually see. So you're probably familiar with the Roy G. Biv, red, orange, yellow, green, blue, violet. They got rid of indigo apparently. And those are listed in order of increasing energy. So red has the least and violet has the most. And then how do we remember that? That's always my problem. I don't know. How am I going to remember that? So here's the little trick I played with myself to remember that violet has the most energy and red has the least. So I remember that next to the visible spectrum on the violet end is ultraviolet. And ultraviolet sounds like it's really super violet, so it must have lots more energy than violet does. So if I can remember that ultraviolet has more energy than violet, then on the other end, I can remember that infrared has less energy than red. So that's how I remember it, but you do need to know that. Ultraviolet light, abbreviated UV light, you probably associate this with the sun because that is where we get most of our ultraviolet light from. Also where we get our vitamin D from is the ultraviolet light hitting our skin. And then of course X-rays, you're familiar with X-rays, that's how you look at your bones. X-rays, I think most people associate those as being very high energy, so that's pretty easy to remember. And then going to infrared, the abbreviation for that is IR, and that is heat. It's the energy that we associate with heat. And what the College Board wants you to know about IR radiation is that it can be used as an analytical tool because it causes vibrations in covalent bonds. They don't really care if you know much more beyond that, really, so I don't usually go into it more than that. When we actually talk about Lewis structures and drawing molecules and covalent bonding and things like that, I can come back to this and touch on it again about what does it mean to have a vibration in a covalent bond. And then lastly, microwaves, which have the least amount of energy in our list. What they want you to know there is that they affect rotations in covalent bonds. And again, it's an analytical tool to use microwaves to help you identify something by looking at the rotations in covalent bonds. But all they really care that you know is that microwave is rotations and infrared is vibrations. And I could never remember that for the longest time until a very clever student pointed out that microwave ovens rotate. And now I remember. Microwaves cause rotations because microwave ovens have that rotating tray inside. So there you go. All right, so you need to know increasing in energy in order, including the Roy G. Biv. And in addition to knowing about energy, we should also know about wavelength and frequency. So as we move from left to right, we are decreasing in wavelength, and wavelength is actually measuring a length. So you could measure that in nanometers or meters. And we're increasing in frequency. Frequency is how often the wave goes by, or how many waves go by in a certain amount of time. So how many waves go by in a second, for example. So that's where we're getting these units of per second, 1/second. So it can be written as 1/second or second to the -1, if you like that better. It's also the same as a hertz. Hz is an abbreviation for hertz. All of those mean per second. So frequency is how many waves go by per second, or how many times does it happen per second. And wavelength is the actual length of the wave, the distance. There are also various equations and formulas on your constants and formulas sheet. So these are all on the sheet. I'm just kind of going over them quickly to point them out. So C stands for the speed of light. That's a constant. And C equals lambda times nu, frequency times wavelength. These two values are not independent of one another. If you know one, you know the other, because their product equals the speed of light. E for energy is the energy of one photon at wavelength lambda, and the fact that it's one photon is an important point. So E equals h nu, and h is Planck's constant. Again, it's on the constant formula sheet. And that is joules seconds, not joules per second, joules times second for that unit. If we use our speed of light formula up there, we can say E equals h nu, and it also equals h times the speed of light divided by lambda. So it's the energy of one photon with that wavelength or with that frequency. So you'll be using these using formulas to calculate things later. All right, so it's easy to see that electromagnetic radiation is a wave. We can talk about light waves and measure their wavelengths and frequencies, and that's easy to understand. It's easy to understand electrons as particles. We can easily visualize them as little teeny tiny spheres zooming around. But the quantum theory views electromagnetic radiation as particles as well. A light particle is called a photon. So we get this photoelectric effect. We'll be talking about that in a minute. That shows us the the particle nature of light. And then we can also view electrons as waves, which it's not very intuitive, but electrons can be analyzed and studied as waves, and we can explain their behavior if we look at them as waves. So de Broglie came up with an equation that can relate the particles to the waves. So we want to look at the dual wave particle nature of matter. How can matter be both a wave and a particle? So all matter can behave as particles or waves. And here's de Broglie's equation. Wavelength, lambda, equals h, that's Planck's constant again, divided by mass times velocity. So this equation relates a wave property, wavelength, lambda, to a particle property, mass, the mass of the particle. In classical physics, that's Newtonian physics, that's things we can see with our own eyes. It's a normal macroscopic scale. So in classical physics, the mass is big and the wavelength is very, very small. It's much, much smaller than the size of the particle. So think about it, if you have a big M, big mass, in the denominator, you're going to end up with very small lambda when you finish the calculation. However, in quantum physics, where we're talking about inside the atom, electrons, atoms, molecules, things like that, now the mass is very small. So when you put a very small number in there for mass, you don't get a teeny tiny lambda or wavelength. Now your wavelength is greater than or equal to the size of the particle. So the wave nature of atoms and electrons really matters because they're on the same scale. The wave nature of baseballs and airplanes and you and me doesn't really matter very much. So I made this slide to kind of compare the wavelength of the particle against the actual size of the particle. So a car, for example, has a wavelength of 10 to the negative 38 meters based on its mass and velocity. But the actual size of that item is on the order of 10 to the 0 meters, which means about a meter. So its wavelength is 10 to the negative 38, and its size is basically 1. I mean, that's tiny, tiny, tiny. Same with a baseball. Its wavelength is 10 to the negative 34, but the size of an actual baseball is more on the order of 10 to the negative 2 meters, so on the order of centimeters. But then you go to the oxygen molecule and the electron, and now the wavelength is getting bigger. The wavelength is 10 to the negative 11 meters, and the actual size of an oxygen molecule is on the order of 10 to the negative 10 meters. So that's more on the same scale now. Suddenly, the size of the particle is actually slightly smaller, sorry, just only slightly bigger than the wavelength of the particle. And then if you look at the electron, the size of an electron is 10 to the negative 16 meters compared to its wavelength 10 to the negative 10. So now the particle is actually much smaller than the wavelength. So the wavelength is now significant. So another way to kind of look at this, this is not perfectly to scale, but I'm trying to give you an idea here. If you look at the baseball is really big compared to its wavelength. Whereas if you look at the electron, it's more on about the same size as its wavelength or slightly smaller than its wavelength. So imagine that that electron is a little boat and it's floating on the ocean, and the ocean's going by with these waves. Well, the boat's going to go up and down over the top of the waves as the waves float by, right? The waves would interact with the electron. But with the baseball, if the baseball was floating upon the ocean and the waves were that tiny, that has no effect on it. It wouldn't even notice as they go by. It would just be riding on top of all of those little peaks. It would not be going up and down and up and down and up and down. So this is not meant to be literal truth. This is just a way of visualizing why does it matter if the wavelength and the particle are about the same size as opposed to the particle is much, much bigger. So we always model a baseball as a particle. It makes no sense and it doesn't help us in any way to try to model it as a wave. But we can model an electron as a particle or a wave, and depending on the experiment you're doing, it makes more sense, or you can explain it better if you look at the electron as a particle sometimes or a wave in other times. So trying to visualize the idea of an electron as a wave, trying to understand an electron as a wave. I've got a couple ways of modeling that for you. So we can view an electron as a standing wave. And by doing this, we can help explain why electrons can only have certain amounts of energy, why electrons are quantized in the atom. So a standing wave is one that's fixed at both ends. So if you look at the picture at the top, that first wave, it's fixed at both ends, the left and the right. So pretend that's a rubber band or a guitar string, and it's fixed on either end. If you pluck that string and start to make it vibrate, it creates a standing wave. So you have a whole wave in between those 2 points. If you then hold your finger in the middle and create a node in the middle there where you're securing the wave in the middle as well. So it's now fixed at both ends and in the middle. Well, now you get 2 standing waves. If you hold down 2 fingers and you fix it in 2 different places, now you have 3 waves, and then 4 waves, and then 5 waves, and then 6 waves, and then 7 waves, but you can only have a whole number of waves because of the way that the rubber band or the guitar string is fixed in place. You can't have half a wave. That's the thing about the standing wave, is you can only have a whole number of waves. So it's like saying that an electron can either have the amount of energy that you get from 1 wave of that wavelength, or 2 waves that are shorter, or 3 waves that are shorter, but it always has to be a certain specific wavelength. You can't just have any wavelength that you want. So only specific wavelengths are possible based on the total length of the string and the number of waves in the string. So you can only have certain energies because energy is related to wavelength. So if you can only have specific wavelengths, either 1 or 1/2 or 1/3 or 1/4 or 1/5 in whatever unit that's in, then you can only have specific amounts of energy for each one of those standing waves. So here's another way to kind of visualize that. Now it's kind of saying, let's superimpose that standing wave over like an orbit, an electron orbit. That's what those little dashed lines are supposed to be. There's my circle of my electron orbit. Well, I can have, depending on the length of a string, for example, I could make that string go through 3 waves or 4 waves or 5 waves or 6 waves. But if it's going to start and stop in the same place every time, then it has to give just a specific number of waves with a specific wavelength. You can't have any old thing you want. So if you look at the bottom picture, see how the string is starting at the beginning at the same place and it's ending at the same place it meets. But in that second picture, it doesn't meet. They don't start and stop correctly. It doesn't meet up with itself properly. So it can't exist that way, is what we're saying. It can only exist where it makes a continuous, complete wave. So I can only have certain wavelengths. I can't just have anything I want if I want it to start and stop properly. So again, this is just a model. We're just trying to have ways of like explaining this concept of how a particle can be a wave and why it helps us explain quantum theory. So don't try to take it too terribly literally. It's just a way of visualizing it. Okay, so because we look at an electron as a wave, Schrodinger calculated wave functions to determine the probability of where an electron can be found. And Heisenberg said that we can't know the location and the velocity of an electron at the same time. So he said there's no circular orbits like Bohr thought. Instead, there's these standing waves. So think of it as I can't know where an electron is at any specific time, just like I can't say where a wave is at any specific time. It's not a point. It's a continuous wave. It just keeps going. How would I say where it is? There is no where it is. It's a probability of being somewhere in this area, but I can't pick a specific spot because it isn't a particle. It's a wave. Okay, so that was talking about electrons. Now let's try to look at energy. Let's look at how energy can be viewed as both a wave and a particle. So electromagnetic radiation, or light, can be considered as a wave or a particle, and a particle of light is called a photon. So the energy of one photon can be calculated from the wavelength of light, and we've seen this equation several times now. This equation, again, it's relating a wave property, wavelength, to a particle property, energy of the photon. The photoelectric effect is an observation that Einstein made that shining a light on a metal surface causes electrons to be ejected from the surface. And to explain the effect, Einstein said that what was happening was one particle, one photon, was knocking into another particle, an electron, and knocking that electron off the surface of the metal. So the photoelectron effect doesn't make a whole lot of sense if you try to explain it as light is a wave. But if you explain it with light as a particle, it makes a lot of sense. So this is kind of a schematic of the photoelectric effect, and you have a whole entire another lesson coming up that explains this more. So you do not need to understand all of the details of it right now. But the idea is that the photon comes in and that photon particle would hit an electron and bounce it out, kind of. So the photoelectric effect is easier to explain if you look at light as a particle, a photon, instead of as a wave. So for example, the number of photons, which is like how bright the light is, the intensity of light is the number of photons. The number of photons is proportional to the number of electrons ejected. One particle ejects one particle. One photon hits one electron and bounces it out. But if the energy of light is too low, then increasing the brightness or the intensity still won't eject the electrons from the surface. You have to have enough energy coming in, and that's to do with the energy of that one photon, that particle. It has to have enough energy to bounce that electron out. So again, you're going to study this in future lessons. You've got a lot of stuff coming up, so don't worry about the details of it right now. So connecting the energy of electrons and the energy of photons, the atomic emission spectra are one thing that does that, and we did study this last year. Last year, this was associated with the FLAME lab, with fireworks, with neon lights. This was Bohr's evidence for the quantized energy of electrons. This was his evidence to be able to say that electrons can only have certain amounts of energy. So the idea was that electrons can gain energy and jump up to a high energy level. We call those excited electrons because they're no longer in the ground state. And then those electrons release the energy as light, electromagnetic radiation, when they fall back down to a lower energy level. And that's the light we see. That's the emission spectra that we see. And the amount of energy released is equal to the difference between the two energy levels that the electron dropped from. And the specific color of the light, which is related to the wavelength of the light, it's a specific color because it's a specific amount of energy, that amount of energy between the two energy levels. So you're going to study this more in an inquiry sheet, and you're just about to do that because that is the classwork that comes after this lesson.